All right, the data that we'll deal with in this chapter involves n coin flips, which we will notate as y1 up to yn. And in our example, in a moment, we'll have n equals 30. And the values yi will either be 0 or 1. 0 for tails and 1 for heads. So if I pop over to our studio and grab data from the book, these data are notated as h and t for heads and tails, but I can convert those to binary with the as numeric function. So my y values are 1s and 0s, and I have n equals 30 of them. All right, let theta denote the probability of heads. So for any I, the probability that yi is equal to 1 is theta, and the probability that it's equal to 0 is 1 minus theta, and theta is a number between 0 and 1. The research question is, given these data, can we determine if the coin is fair? In other words, is theta 50%? Whoop. So I want to test the hypothesis that the coin is fair. There are 3 ingredients in any hypothesis test. The first ingredient is the model for the data. The second ingredient are the hypotheses involved in the test, null and alternative hypotheses. And the last ingredient is the choice of a statistic. And I will cover these 3 ingredients in turn. Okay, so the model, ingredient 1, that's our probabilities for the coin flips. And the notation for that is like this. We say that y comes from a Bernoulli distribution with parameter theta for each of the n flips. The Bernoulli distribution has a mass function that looks like this. And you'll notice that if you plug y equals 1 into this mass function f, you get theta. And if you plug y equals 0 into the mass function, you get 1 minus theta, just like the probabilities we wrote down on the first page. So this is our probability for y with parameter theta. If we assume that coin flips are independent and identically distributed, we can use that independence to look at the joint probability of any 2 coin flips, yi and yj. Those probabilities will factorize into the product of the individual probabilities. So if we looked at all n probabilities jointly, those would factorize as the product of n separate probabilities, each with a parameter theta. And we can write out that mass for all n of them as the product of the individual masses. And if we write out what that mass looks like, Then we get a formula that we can simplify by bringing the product into the exponent as a sum. It'll be handy to have this tidy expression later. So that is the model. Ingredient 2 are the hypotheses. We want to know if the coin is fair, so our null hypothesis will be that the coin is fair, and the alternative hypothesis is that the coin is not fair. That's the end of that. That one's pretty simple. The third ingredient is the choice of statistic. The technical definition of a statistic is any function of the data values. Although the statistic is your choice and any function will do, just as the hypotheses are your choice and the model is your choice, once you've determined the model and the hypotheses, a good statistic naturally suggests itself. We can look at how is the data involved in the model using the parameter in the hypotheses. So notice how we're using the model and the hypotheses to determine the statistic. Let me remind you of our joint mass. Look at how a function of the data is involved in the model and in the parameter involved in the null hypothesis, theta. So a good statistic is this sum, S of y is the sum of the y's. Let's go back over to R and calculate our chosen statistic. So S is the sum of the y's. So there were 18 heads in these 30 coin flips. Now we have all three of our ingredients. How do we conduct a hypothesis test? So we have the ingredients. Now, how do we put them together to bake the cake? Assume that the null hypothesis is true. The coin is fair. So this involves ingredient number 2. Generate data, which I'll put in quotes, from the model. So that is ingredient 1, using what you assumed about the null hypothesis, which was the previous bullet. Then calculate the statistic with those data. So that's ingredient 3. And then repeat. That is a really important ingredient. I'll show you what I mean when we get over to the code. And then compare what you got from that simulation to the observed value of the statistic. Okay, so let's do that. So assume that the null hypothesis is true. So I'll just write theta is 1/2. Okay, that's what the null hypothesis says. Generate data from the model using the null hypothesis. I can do that in R with our binom. If I give our binom the number of flips I want and the number 1, the reason for the number 1 is talked about more in the book, but just take it as given for now, and then give the parameter theta. Each time I run this, I'm going to get n, which is 30, virtual coin flips data under the null hypothesis, which is that theta is 1/2. Each time I run this, I get a different sequence of 1s and 0s. These are my virtual data, or I like to notate them as my simulated y values. I remind myself that they're simulated by putting an S and capitalizing the y vector. Then calculate the statistic with those data. So I take the sum of those virtual y's. Okay, and each time I run these two lines, I get different 1s and 0s, so I get a different count of the number of heads. Here I'll do it a third time. Now we come to the repeat part. So what I'm going to do is I'm just going to go up here and write repeat all that. So I'll make a for loop for I in 1 to capital N, and I'll define what capital N is. So I'm going to repeat it 10,000 times. Okay, and then I'm going to grab those lines of code and put them in the loop. Now that's going to repeat that over and over again, and I want to save these statistics that were simulated in a vector called SS. So now when I run that for loop, it was very fast, even though it was doing 10,000 different things, giving me a bunch of sampled or simulated statistics under the null hypothesis of coin flips from a fair coin. And now I need to do the last step, which is compare to the observed statistic. So now I have to be a little bit creative about how I want to do that. I'm going to use a histogram to visualize my sampled sums. Now you can't see that because the plot is being covered by the notes. So let me reveal the plot for you. So there's my histogram of those sampled S's, and then I can make a comparison by putting the observed value of the statistic on the plot. And I'm going to make it red, and I'm going to make it bold. So there is the value of the statistic, which was 18, placed on a summary of the distribution of the statistic. This is called the sampling distribution. I'll put that here. Or the null distribution. Some people call it that, because it uses the model along with the null hypothesis to show you what the distribution of the statistic is, its sampling distribution under the null. And this is the observed value of the statistic from the data without quotes. Now it's up for you to determine if the observed is similar to the virtual. or the hypothesized. The way that statisticians like to make that comparison is quantitative. Statisticians prefer quantitative comparisons. When I look at this, I think this is the main story. I see that I could have gotten more heads, 20, or maybe even as many as 22 or 23, a decent proportion of the time. Eyeballing it, it looks like I would get numbers of heads bigger than 18 about 15% of the time, just kind of looking at it. And since I would be just as surprised to see the same number of tails as I would see the number of heads, because there's really no difference between a heads and a tails, the chances that I would see more extreme numbers of heads and tails is closer to 30%, because I've got the part of the histogram that's over here at 15%, but the tails part of the histogram also has 15% on the other side. The way that that statisticians, whoops, I do want to do that. I'll go back over to the notes here. Is statisticians like to calculate what's called a p-value. So a p-value is one way to make a quantitative comparison. The definition of the p-value is the probability of observing a more extreme value of the statistic than the one you observed from the data. Okay. So going back to our example here, I could count how many virtual stats were bigger than the observed one. So that's the sum of the y's bigger than the observed. I must have made a mistake. Oh, not the y's, sorry, the statistic. Sum of the number of statistics that's bigger. So 18,000 of, sorry, 18,000, I must have done 100,000 soon. I did 100, I said 10,000, but I did 100. 18,000 of the 100,000, so 18% of them would be in this tail. So it's like we're integrating into the tail of the distribution, but I can do that integral with the sum because I have 100,000 discrete events. So that could be my p-value right there. But if I want to acknowledge that I would be just as surprised at getting that number of tails, so I'm trying to be symmetric about 50%, which is my null hypothesis, I could multiply that by 2 and get 36%. Another way to get the same number is with the mean command, because the mean will take care of the sum and the dividing by capital N. So you get the same number that way. So this is the probability of observing a more extreme sum of the y values under the null hypothesis. So it seems that 36% of the time, that seems like a lot to me. I think that seeing so many more extreme numbers of heads or tails when the null hypothesis is 50%, it tells me that the 18 that I got is not at all extreme. So I will conclude that the coin is fair. Most statisticians would use 5% as a threshold. 0.05. So if your p-value, we'll go back to the notes on this. If your p-value is less than 0.05, then you reject the null hypothesis. Otherwise, some people would say fail to reject, or accept is also fine, the null hypothesis. And that completes the story of Chapter 1.